So which test did you use here on this first one? I guess maybe we should start by shooting from the hip on this first one. Like what does this feel like, and what do you think? Does it converge or diverge? And why is that even a question? A couple people even asked me like, why is there even any question? Of course it converges. There's no infinity involved. Why is this maybe an improper integral? Is it clear why this is an improper integral? Because we have a vertical asymptote at t equals 0. Yeah. Okay. So with that in mind, let's return to the question: what does this act like, and what do you think? Does it converge or diverge? It kind of feels like what function? 1 over root t, which on the interval 0 to pi, 1 over root t converges, actually, right? We had that as one of the results that we talked about yesterday. We just kind of hinted at the proof, but we didn't actually say, maybe we said like maybe consider the inverse or kind of have that conversation. But we did state the result that on that interval 1 over root t would converge. So it would be like kind of done if the sine t wasn't there. So I think all of us have this intuition that this function, just like 1 over root t, converges also on this interval. So now we just need to kind of like formalize that somehow. Michael?
Why can you ignore sine t if it's on such a small interval?
Yeah, that's a good question. So
there is a reason it goes from 0 to pi because beyond pi then sine t can become negative. Because it's from 0 to pi, you can always assume that 1 over square root of sine t is less than.
Yeah, maybe this is actually helping us on this interval, right? The fact that 0 to pi is involved. Like sine t is always positive for these values. Is that, like, that actually makes a difference here, maybe. That was a helpful comment from Alon. Does that clear things up? All right, so yeah, let's compare with 1 over root t. Maybe we can just do a direct comparison then and be like done with it based on what he said. Is that a good way to do it? There's no shame in doing the limit comparison test too, but I think we can just do direct comparison on this one. So again, and some of you were asking in the homework as I walked around, some of you like just wrote like not very much. So let's make sure we actually, I tried it on yesterday's PowerPoint, like put quotes around. So like this is the kind of thing we're expecting to write, and I'll try and demonstrate that here again, right? We might say, since the integral 0 to pi of 1 over root t dt converges, and then in parentheses I might write, because p is equal to 1/2, which is less than 1. And for all t in this interval, 1 over root t is greater than or equal to, it doesn't matter, root t plus sine t. Again, for t in this interval, right? Then, since, I'm going to make sure my grammar is right, since this converges and that's true, then this also converges, right, by dct. So this is the kind of thing I'd like you to write. Right? I think every element really has to be there, whether you use a different set of grammar or not. I think we should have like words. Right? You should like describe what's going on and have a period at the end. So something along those lines, yeah. Yeah, because it doesn't exist there. Is that better? Yeah. Interestingly, I mean, the convergence or divergence of an integral maybe doesn't matter at a point, really. So we could have it on both ends if we wanted to. But yeah, I think you're right. We shouldn't put a hard graph there. All right, so maybe the first one was harder of the two. Did you get the second one fine enough? What did you compare that to? Yeah, 1 over x to the 3/2 is probably what I would compare this to. 1 over x to the 3/2. So what's your hunch on the interval 1 to infinity? What does this do?
That goes to 0. Oh, goes
the integral of this, excuse me, right? The integral of this converges because 3/2 is bigger than 1. So I have a hunch that this converges too, so I'm just like gonna go for it. I'm not maybe, I mean, can I convince myself that this is greater than or less than that? I might reach for the limit comparison test on this. Just because, yeah, in fact, I think maybe it's always, I mean, I don't know, and maybe I just haven't thought about it enough. It just looks messy, and I'm interested in doing the limit comparison test. But certainly, the limit comparison test works even if it's always less than. You know, we can do that too. So I think this converges. Let's write it out. So since the integral from 1 to infinity of 1 over 3, x to the 3/2 dx converges, and again, because p is equal to 3/2, which is greater than 1, and now we have to do the limit comparison test here. Can I fit it in here? Let's see if I can do it. And the limit as x goes to infinity, I'm gonna hope, if I did this right, I'm just gonna hope. Otherwise, I can go back and erase. It's okay. That when I stack these two, the limit comes out to a constant that's in between infinity, in between 0 and infinity, exclusive. Okay, I'm definitely not going to have enough room here. I'll come down here. So we have some algebra to do right now. So if we flip this up to the top, what do we have? We have x squared over x to the 3/2, and we have a root x plus 1 on the bottom. So what can we do there? This is 1.5. So what does this come out to be here? This is just a root x on top, right? If you want to see it this way, that would help, right? You could maybe write it as this. And what's the limit of this thing inside the radical? 1. Okay, and that's in the interval 0 to infinity, open interval 0 to infinity. So, since that converges, and we really do have to do all this work. Since that, then I'll just write our integral, just because I'm running out of space here. Converges also. By LCT. Okay, so I know we rushed at the end of class yesterday to say something about the LCT, and now we've come out and said it a little more clearly. Here it is. What we've just done is we've just showed that the LCT shows that these two functions grow at the same rate. If it comes out to a constant, in this case it came out to 1, then that shows that these two functions do in fact, we picked it right, they do in fact grow at the same rate. If this converges, then so does this. If this diverges, then so does that. So that's how this goes, and you should write all of that with a period at the end. Tyler, yeah.
Okay, I compared it to y equals x, because y equals x is always a divergence.
And did like a direct comparison or something?
I did a
maybe?
limit comparison.
Okay, all right.
Is that like legal? Is my question? I can't
Yeah,
do that.
what did you get as your limit then?
Infinity, which means that since y equals x diverges, the other one converges.
Yeah, there's the limit comparison test is a little more broad than, but I just need to think about what I need to say here. The limit comparison test is a little broader than I talked about yesterday. If you stack two functions, f and g, and you take the limit as x goes to infinity, then what can we say? Certainly if we get infinity, then f grows faster than g. So that means that if g happened to be like a divergent function, a divergent integral, then f would be too. So we can actually say some things here too, right? Because f grows faster than g, and g diverges, so therefore f does, right? So,
Would you always compare it to a known convergent integral?
okay, yeah. What about convergent? Like, what if we you used y equals x, and what'd you do? Which way did you stack it?
I put x over the other one. I put the known over
okay, you did 1 over x over this thing. And you got,
I did x over
You got-
this weird integral.
you got infinity in the end, right? Yeah. So that tells me that 1 over x grows faster, right, than this function.
I used x.
Like the numerator dominates. 1 over x grows faster, or I mean, out at infinity. Like as you take the limit, as x goes to infinity, that function you just said diverges. 1 over x over this whole thing, that stack goes to infinity. So that means 1 over x, even though I know it goes to 0. But
Well, I used x, not 1 over x.
okay, well then it definitely diverges. Yeah. But what does that tell you about this function, about its convergence? You have a function on top, of course it's going to grow faster. If it diverges, then we have on the bottom a convergent function, a convergent integral. And of course that will happen. But I think there are other helpful things we can say when we see this stack. Like for example, if I have let's see if I can say this right. If I have a convergent function on top, a function that has an integral that converges on top, and on the bottom I put an unknown function and it goes to 0. Let me see if I say this right. No. And it goes to infinity, then what we've just said is that g grows slower than f, and f converges, so therefore g would converge too. So we can actually use the test a little more broadly, but the way we advertised it yesterday was like, let's just go for a constant, and then we've like matched it perfectly, right?
So you're saying infinity was constant?
No, a constant in between 0 and infinity exclusive, in the open interval 0 to infinity. So yeah, and actually I think the book, when we will say some more about the comparison test as we go on, and I think they have it phrased in a slightly more broad way too, actually, than we said yesterday. So we'll get into that too. So hopefully, like I said, even though we rushed at the end of yesterday to say a little bit of some of this, but this hopefully just doing these 2 examples, which are pretty interesting and deep, clarifies some of what we said yesterday. Okay. Today's will be a little bit of a nice respite from yesterday. Yeah, in. It just means in. For t in this interval, right? Did I see another hand somewhere? Okay, so I think these are great ways to do these problems. Okay, so we'd like to start talking about start talking about infinite series today, and instead of integrals, right? We're actually not going to see an integral at all today. Okay, and you just have to kind of trust us that series matter for us. And maybe you've already, for those who have studied series, you're already feeling like this is all familiar, so you maybe already see where this was going already. But today we're going to just lay the foundations a little bit and talk about series, in particular infinite series. And you'll remember from pre-calculus the difference between the word sequence and series. What do we mean by a series? We mean a sum, right? And really series should be just synonymous in your mind with the word sum. Okay? Like for instance, it makes grammatical sense to say evaluate the series. It makes no sense to say evaluate the sequence. That doesn't mean anything. The sequence is just a comma-separated list of things. The series, though, is the sum of things. That is, it's an expression of this form. And of course, in this class, really the series we're interested in are these infinite series. And you'll see why very soon. Good. So you could write it compactly in this summation notation form that you're used to from pre-calculus that we'll use time and time again here. But you could also use it this way using triple dot notation, right? They mean the same thing. One is a little more compact than the other, okay? So that's one advantage, I guess. We would call the terms of this, we talk about each A1, A2, AK as being the terms. And we might say that AN is the nth term, or up there, I guess AK is the kth term. So just to practice from pre-calculus here, can we write this in summation notation? Let's just practice using summation notation. And we should also just say, too, that there's not a unique solution here. You could write this a couple different ways compactly. We give everyone a second to do that, then. Just to remind ourselves. I tried to make it as terrible as possible. It's got all sorts of things going on. Don't say that. Give Ryan a chance to think. I'll do this part for you. There you go.
Oh, that was a hard choice.
I know. It does take practice to draw that. I'll give you another part for free. Here you go. There you go. You're welcome. Okay, who wants to be my friend right now? Anyone want to be my friend? Jack, you want to be my friend? Okay, talk out loud with me here. Okay, so what do you see on the top?
Well, on top it looks like 5dx.
Okay, and right away, and by 5dx, we usually reserve like x and y to be variables that represent continuous things. So maybe we use a different letter. What's a kind of letter that you're used to using with series of sequences? I is good, N is good, K is good, J is good. What do you like, Jack, of those? What do you want? N is great. M is good. Things near the middle of the alphabet is usually what mathematicians like to use. Okay? No, we don't usually use Y. Tradition. Okay. I don't know. It's just tradition. All right, so right away you've also made another choice then too, Jack. We're still friends, okay. You also made if this is the first term, then you're also dictating that n starts with what? 1. You made that choice. It's okay. It's perfectly good. Okay, I just want to make sure. Okay, I'm going with Jack here on this. All right, and then do you want to keep going? Do you want to talk to me about other things?
8n times possibly like n plus something factorial.
So this is like a 1 and 8, a 27.
N plus 1 factorial.
Oh, this piece here?
Yeah, and then 8n on the left.
8n. Let me just test that because I don't know.
8n minus 1.
8n minus 1. Okay, let me think. It's
No. Oh. N cubed.
n cubed. So 1 cubed is 1. 2 cubed would be this.
Oh, that's
3 cubed, 4 cubed. Okay, those are okay. I think I like that. N cubed. And then we do have something factorial. I have to think about it though. It's like it's the odd numbers. How do I do that? Say it one more time, Mac.
K plus K minus 1
K.
N, yeah, sorry, not K.
N plus n
Yeah.
time plus n minus 1. Is that what I just heard you say?
N, yeah, plus.
All right, or AKA
I don't know.
2n minus 1.
Oh, yeah.
One way of saying what the odd numbers are is that they're the even numbers. Minus 1, right? It would be one way of saying what an odd number is. Okay, but if you need to go through the work of doing it, it's an arithmetic sequence: 1, 3, 5, 7. And if you hand that to like an algebra 1 student, they should be able to come up with a rule for that, right? Okay, so yeah, you might just not have, but you can also maybe just do it in your head too, whichever. So that looks pretty good. There's one little snag, maybe. There are some pluses and minuses. How can we get those in the mix, Andrew? Yeah, how do we get an alternating sign to happen? I like the something to a power idea.
Negative n quantity cubed.
Negative n cubed. Oh, careful, that will always give
Oh, sorry, so negative n.
Yeah, I don't know if I like this. I want n to be the controlling power, maybe, right? Yeah, Elizabeth? Multiply everything by negative 1? Well, but then it's all negative, and we want some of them to be positive, every other. You got this?
Negative 5 p.m.
I like it.
If you have 1,
Oh, wait, yeah, except for n equals 1, so we need to, like, maybe just throw a negative out front somewhere? There, everything's better. Okay, I don't know. That's fine. That works. All right. Just verify that works. Plug in n equals 1, plug in, like n equals 2, and see that this is actually working. By the way, this is not the unique solution. If you wanted to, could you write this all in terms of n equals 0 as the starting index? Sure, you could. Yeah, so this would be then 2n plus 1. This would be n plus 1 cubed. This would be negative 5 to the n plus 1, and you wouldn't need the negative 5 there then. Or, yeah, you would still. Okay.
It'd just be two, wouldn't it just be 2n instead of 2n plus 1?
You wouldn't need it there anymore, yeah.
It would just be 2n.
We struggled our way back.
This here?
Yeah, instead of 2n plus 1.
It'd be 2n plus 1. Because we still want the odd numbers, but we start with 0. Yeah. All right, so there are other ways to write that, for sure, that are correct, but I like that way right there. So good practice in summation notation. Like I said, I tried to give you like the hardest one I could think of. There's just all sorts of things happening, alternating signs. Got something cubic, something factorial, something exponential. All right, and then we want to talk about whether something like that, notice I didn't ask you this question, does that converge? Does that even mean anything, that last one? I think on the last one the answer is like, yeah, and the answer, what does it converge to? The answer is I don't know on that, right? But maybe it does, maybe it doesn't. These infinite series, we have this question, same kind of question we've been asking recently, which at least hints at a relationship between these two ideas. We don't know sometimes whether these converge or diverge. So the idea can be formalized by thinking about this sequence of partial sums, as people say. And by the partial sums, we mean, let's stop and talk about these things that are well-defined. For any given fixed ending for our sum, we have something that definitely is a finite number, right? We can add up the first 1,000 terms even if we like. And what we would call that for any fixed value is a partial sum. That's a good word for it, right? Because it's not the whole sum. So that's what you're looking at here. And if we talk about, if you tell me the sum of the first term, the sum of the first two terms, and you label those sums S1, S2, S3, what we have is like a new thing that's been generated from our sum. It's called a sequence of partial sums. And the question is, do those, if you add up the first one term, the first two terms, the first three terms, the first four terms, the first 5 terms, etc., the first 1,000 terms, the first 1,001 terms, the question, does that number that you get in your sequence, that is the partial sum that you get, does it converge to a value, is the question. And if so, then we say that the infinite series converges. Said very, very compactly, we can just write this, of course, right? How do we make sense of this symbol on the left where we have a sigma with an infinity on top? The answer is, well, we kind of take the approach we just did recently with improper integrals. We don't know what this means, but we do know what this means for any finite n value. So tell me what that is. And then take the limit of that as n goes to infinity, right? So again, in fact, actually, I think that's like something I would have put up, at least in my pre-calculus class. I think I put that exact thing up there. So it's not necessarily news to you, but I just want to remind you what we mean by an infinite series. And what we mean by an infinite series converging. Okay. So I think we're finally ready to like talk about how to like do some series testing for convergence. And by the way, even though I've like been speaking passionately, most of I think what we're doing today will be review, and I'm just gonna like come out and acknowledge that. Isn't this fine with me? Just fine with me. That's all it is. Because it was hard last year, and you're really, really gonna need to know it this year as we keep going, right? So like it's a good foundation to set. Go back, you said. So let me refresh your memory on a couple convergence tests. It's really, actually, maybe don't even look at the second two as I put these up here. The first two are the ones I want to mention, and we'll use mainly today. So the first one might be the nth term test for divergence, and I like saying that whole thing in one breath, the nth term test for divergence, for reasons we'll say in a second. The first thing to say is if you have terms of your series that are not approaching 0, then it definitely diverges. Like, if the terms of your series approach 1, then what does that mean? It means out in infinity, it's basically like you keep adding 1. Well, definitely, the sum of those numbers will definitely not converge. So we require for a convergence series that the terms themselves, that is the sequence of terms, goes to 0 in order for there even to be a chance at convergence. Now, the reason I say it's the nth term test for divergence, and I like saying all of that, is that can you prove that a series is convergent by this? And the answer is no. If you remember this from pre-calc, maybe you've heard about that before, right? The answer is no. You can't prove convergence ever using this. Don't you dare try. So you might say the statement is true, but is false. But the converse is not necessarily, doesn't hold necessarily. All right, another thing you would have learned last year is the geometric series test. If we're going to identify a series as being geometric, that's beautiful, because not only can we really clearly say whether it converges or not, and I'd love to spend time developing, like, why is it that it's r less than or greater than 1? But I assume maybe you thought about that last year a little bit. Like, why is that happen? And furthermore, we can actually say what the sum is. Like, if this is a pre-calculus class, we would spend a whole period like proving that, right? That it's a1 over 1 minus r, the first term, divided by 1 minus r, where r is the common ratio. So that's pretty cool. So I think you'll remember that, at least vaguely, right? That we can do that with a geometric series. The geometric series are awesome. And then we'll just put these other two up here just because we've talked about them recently, okay? But please don't copy them down just because we don't have the time. I'd like to do a couple examples. But these two, feel free to copy down because we haven't talked about them recently. But certainly it's true that still the direct comparison test and the limit comparison test still work. And we don't actually completely know, like, maybe we need to stop and prove those for series too. Maybe there isn't an automatic transfer of knowledge. Maybe we need to think about that relationship. But we did talk about them recently, and they do work exactly the same way, promise. Okay, and then my goal is to like do as many. That's like the notes, but no, we get to do as many examples as we can here. Show you a few series. Did everyone get a chance to write these first two down? I want to make sure, or if you're writing them down at all, I don't know. Eventually, I've had this request before. We're going to give you a ton of different tests. So I think we will try and produce some kind of sheet for you that has them all. Your book has them all too, but we gave you a sheet last year in pre-calculus with some of these on it. All right, let's talk about a few series now. Like, I want to just do as many examples as we possibly humanly can in 5 minutes. Does this series converge? What do you think? Let's go with intuition first, maybe. What does it mean for a series to converge? It means we have 1 as our first partial sum. If we add up the first 1 term, you get 1. If you add up the first 2 terms, you get 0. If you add up the first 3 terms, you get 1. If you add up the first 4 terms, you get 0 again. And my question is, does this sequence, that is the sequence of partial sums, converge? And the answer is no. It doesn't converge. You could say it converges to 0, or you could converge to 1, but it doesn't converge closer. By converge, we mean like it gets closer and closer to a number, and you can demonstrate a point at which it never leaves outside of a band around that number, right? So if you claim it's 0, then I want you to find me a place after which it always stays within any arbitrary distance of 0. And you won't be able to do that with this one, right? That doesn't get closer and closer to 0. That's wrong. So this diverges. It's actually, we've never stopped to define a limit ever, but that's actually the definition of a limit. Yeah. We just don't, anyway. But you could say it's by the end term test if you like. The terms themselves don't go to 0, do they? What about this one here? Yeah, well, the first thing to do is maybe, I would probably always reach for the end term test first just because it's like pretty quick to see. Do the terms go to 0 or not? If the terms go to 0, then we need to do further testing. But if they don't, then we're done. That's a beautiful first gateway, right? So on this one, the terms themselves, which have the form what? Yeah, 1 over 2 to the n, where n starts with 0. If you want to, you could index that however you like. But yeah, definitely, if you look at this term, the terms do go to 0. So we don't know by the nth term test, but of course this is what kind of series? Yeah, it's geometric. And if we can say it's geometric, then we can also write down what the first term is. It's 1. And what the common ratio is, it's 1/2. And we know that if it's 1/2, then it's less than 1 and it converges, right? So this converges by a geometric series test. With r is equal to 1/2, which is less than 1 in absolute value. And the sum is, I heard some people say, 1 over 1 plus minus 1/2 which is 2. So it's very special. It's not necessarily always the case, but it's very special when we can say the sum. It's pretty cool. So there it is. So do a couple more here. See if we can do another one or two before the bell rings. Does it converge or not? What do you think? What kind of series is it? It's geometric. And what's R? Looks like every time we're multiplying by 3/5, right? Which is less than 1. So it converges. What's the first term? If you plug 0 in? 2. So the sum is 2 over 1 minus 3/5, which is something. That's 2/5 on the bottom, so is it 5? Did anyone get the next one yet?
The RCA interest meeting is taking place now in room 33. Also, softball practice will end today at 5:30 due to cold temperatures. Please make sure you
All right, bye guys. Do your book homework tonight.
The Spirit Shack will be open today during lunch. Go check out the new merchandise now. For the following students, please come to the main office. Johan Herrera, Elijah Jenkins, Amani Maywana Johnson, and Roxana Lacco.
And term test.
Yes.
Those are getting bigger and bigger too, so it seems pretty obvious.
Yeah. There's also one other interesting thing about that one, and that's that